pattern in the Pythagorean's theorem is to let the radical exist on the hypotenuse. So if we have a side A and a side U to be the differential quantity, then the hypotenuse is the sum of the squareds and then the square root of that. And so looking at this, what we want to do is we want to set up the tangent ratio relative to theta. So we know tangent is opposite over adjacent, and the opposite and the adjacent are the two legs that, and they happen to be also the two that have the simplest expressions on them. And then and we also know that when we talk about tangent in terms of taking derivatives and substitution, we also talk about tangent hand in hand with secant, because those two trigonometric ratios show up in other trig identities. So we can go ahead and set up the secant ratio then. And of course, just to remind you that the secant is the reciprocal of the cosine. So the secant theta is 1 over cosine theta. To set up this integral, the substitution for this integral, then if we draw a right triangle here, see if I can insert a right triangle shape. There we go. So if we draw a right triangle shape, there we go, where we have our theta down here and our right angle right there, then if we see this pattern here, we need to get this pattern into u squared plus a squared. And that being the case, then this u squared ends up being 2x quantity squared. That'll give us our 4x squared. And the a squared ends up being 4 quantity squared. So we have our 2x over on the opposite leg and our 4 on the adjacent leg. And so our substitution then looks like setting up tangent of theta equals opposite over adjacent. So that solved for x looks like 4 tan theta over 2. So we know that x is then 2 tan theta. And then when we take the derivative of that, dx ends up being 2, and the derivative of tangent of theta is secant squared theta, d theta. And then we need to set up the hypotenuse here. So the hypotenuse ends up being the 4x squared plus 16. And so setting up the secant for that, we know that, let's see if we can just kind of scoot this out of the way. There we go. We can set up then our secant of theta. If you think about this, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So that ends up being 4x squared plus 16 over 4. And so the expression for the radical then, 4x squared plus 16, ends up being the solution to this. When we multiply both sides by 4, it ends up being 4 secant theta. And so now what we have is we have 3 different expressions to substitute out our values in our integral. So for x, we're going to substitute in 2 tan theta. For dx, we're going to substitute in 2 secant squared theta d theta, and for the radical expression, we're going to substitute in the 4 secant theta. So our integral then looks like this. We still have the 1 here. We're not substituting that out. For the dx, we're going to put in 2 secant squared theta d theta. So 2 secant squared theta d theta. For the x, we're going to stick in the 2 tan theta. And for the radical, we're going to stick in 4 secant theta. And then we can go ahead and simplify this. Okay, so in simplifying this, we end up having the integral of, and let's see here, we've got a secant on the denominator, and that cancels with 1 in the numerator. We've got a 2 here that can cancel with a 2 here, and so we end up with a 1/4. I'm going to pull that out front. That's that, and then we end up with a secant theta in the numerator and a tan theta in the denominator. And neither of these have powers associated with them, so to use trig identities to either convert secants to tangents or vice versa wouldn't work well. So that being the case, then what I'm going to do is I'm going to try substituting this into sines and cosines and see if that gets us a friendlier expression. So we have that, and simplifying this gets us an expression that looks like 1 over cosine theta times cosine theta over sine theta d theta. And so we end up integrating 1/4 1 over sine theta d theta. And if we further simplify that, we're going to have to integrate cosecant theta d theta. And that's a front of book. That's a front of book exercise. So we know that the integrating the cosecant of theta ends up being opposite the natural log. So opposite the natural log of the absolute value of cosecant theta plus cotangent theta. So cosecant theta plus cotangent theta plus c. So we end up having minus 1/4 times the natural log of cosecant theta plus cotangent theta plus c. And we have to get that back in terms of x. So if we go back to the top of this where we have this sketch here, and I'm going to go ahead and try to copy that and bring that down to the bottom so we can do our substitution and look at that at the same time. There we go. Let's try to drag that over to the again. There we go. So if we take a look at setting up the cosecant ratio now, we end up with 1/4 natural log of, on cosecant is the reciprocal of the sine. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So we have the hypotenuse, which is 4x squared plus 16 over 2x, plus the cotangent, and cotangent is the reciprocal of the tangent. If tangent's opposite over adjacent, then cotangent's adjacent over opposite. So this is 4 over 2x plus c. Here's another example of a Pythagorean type pattern falling into the u squared plus a squared sort of pattern. And so I'm going to go ahead and get another right triangle set up here. And go ahead and get this labeled with theta and the right angle. And then again, we know this is the expression along the hypotenuse, is 4x squared plus 9. And so one of the legs is going to be 2x, one of the legs is going to be 3. And so the adjacent leg is what we leave as the a value, so to speak. It solves more nicely when we put it in the expression for the tangent. So if we set up that tangent theta ratio where it's opposite over adjacent, then this solves for a much nicer expression for x, since x is in the numerator. So we end up with 3 tan theta over 2. And then if we take the derivative, dx, we're going to have 3 halves times the derivative of tangent theta, which is secant squared, theta, d theta. And then if we set ourselves up to solve for the hypotenuse here, we want to use the hypotenuse in the adjacent. And that would be adjacent and hypotenuse is typically cosine, we think of it as, but in this case we're going to take the reciprocal of that and we're going to solve for secant, because it's the secant and the tangent that are related to each other in terms of trigonometric identities. So if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. So that ends up being 4x squared plus 3 over 3. And solving for the radical expression, then we get 4x squared plus, 4x squared plus 9. I said this wrong up here. That should be 4x squared plus 9. So solving for that, we get 4x squared plus 9 equals 3 secant theta. And then likewise, we're going to take this and we're going to substitute out an expression for x. And we see an expression for x to the 4th here. So we're going to have this expression to the 4th power. Our expression for dx is going to take the place of the differential here. And our expression for the radical is going to take the place for this numerator up here. So we have then in this expression 3 secant theta in the numerator. We have x to the 4th power in the denominator, so that's this to the 4th power. So we're talking about taking this entire expression, 3 tan theta over 2 to the 4th power. So we'll have to figure that out algebraically. And then our dx is our 3 halves secant squared theta d theta. So there are the substitutions, and when we look at the evaluating the expressions, just in terms of the numeric expressions here, we have in the numerator, we've got 3 and 3/2, so we've got 9 over 2 secant cubed theta d theta. In the denominator, we have 3 to the 4th power, so that's 3 times 3 times 3 times 3, that's 81. And 2 to the 4th power is 2 times 2 times 2 times 2, that's 16. 10 to the 4th power, so we have that expression there. And just looking at these numbers, I'm going to pull both of those out front and go ahead and evaluate that. Leave the trigonometric expressions in there, and we'll evaluate that in just a second. So simplifying here gets us 1 and 9 and 1 and 8. So we end up with an expression that looks like 8 over 9 times the integral secant cubed theta over tangent to the 4th theta d theta. And again, I'm going to convert these to sines and cosines. Instead of trying to use the secant and tangent rules, I just find the cosine and sine rules a little easier to follow. So we'll call that 1 over cosine cubed, and this is sine to the 4th over cosine to the 4th. So simplifying that gets us 1 over cosine cubed theta times cosine to the 4th theta over sine to the 4th theta d theta. And simplifying that then gets us 8/9, and we've got some canceling here, so we end up with a cosine in the numerator and a sine to the 4th power in the denominator. And that makes for a very nice u sub. So if you follow all of the substitution that's going on here, first we substituted out x in terms of theta, now we're substituting out theta in terms of u. So we're going to have to do a double substitution back in to get in terms of x. So we're going to let u be sine theta, which means du equals cosine theta d theta. And so this ends up being then 8/9 times the integral of the cosine theta d theta is just a du, and we have a u to the 4th in the denominator, and so that's a u to the minus 4. And if we think about our powers, so that's going to integrate to minus 1/3 u to the minus 3. So that is 8/9 times negative 1/3. Actually, let's evaluate that right away. So 8/9 times negative 1/3 is negative 8 over 27. U to the minus 3 plus c. And so now we have to start our substitution again. So for u, we're going to put in sine theta. So this is negative 8 over 27 sine cubed theta is all in the denominator because that's a u to the minus 3. And really, sine cubed theta in the denominator is the same as cosecant cubed. So now we're back in terms of theta. And if we go back up to the top here and grab our right triangle for that trigonometric substitution, and we paste that down here. Then we can see that, okay, we know the cosecant is the reciprocal of the sine. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So we end up with negative 8 over 27. So this is hypotenuse over opposite, so it's square root of 4x squared plus 9 over 2x to the third power plus c. And you could just leave the answer like that, or you could simplify it if you wanted to. For instance, if we cube all of this, we're looking at 4x squared plus 9 to the 3/2 power is typically how we do that. We don't usually write a radical in a power. And then the denominator here is 8x cubed. And then you can do some reducing here. The 8's cancel. And we end up with 4x squared plus 9 to the 3/2 power with the negative sign out in front of there over 27 plus c, which is in all likelihood how you would see that answer if you were looking for it in the back of the book, 27x cubed there in the denominator.